So, as machine learning practitioners, we spend a lot of time just staring at raw, chaotic data, right? We rely on these complex models to find patterns for us. But sometimes, the most elegant mathematical solution is actually the most intuitive one. It really begs the question, how exactly does a machine learn to look at a mess of data and build a clean, structured decision-making flowchart from absolute scratch? Well, let's dive right into it. Welcome to today's explainer. We're going to completely demystify how decision tree learning actually works. We'll be pulling from Andrei Burkov's brilliant The 100-Page Machine Learning book, and specifically, we're zeroing in on a fascinating piece of logic called the ID3 algorithm. My goal today, to walk you through this structural approach so you leave here understanding exactly how the machine builds its decision framework, step by step. Here is our roadmap for this explainer. 1. What is a decision tree? 2. The ID3 algorithm process. 3. Splitting the data. 4. Entropy, measuring uncertainty. 5. When to stop growing. And 6. The big picture.
All right, section 1. What is a decision tree?
By definition, a decision tree is an acyclic graph used to make decisions. Now, acyclic is really just a fancy way of saying it doesn't loop back on itself, okay? It flows in exactly one direction, from top to bottom. Think of it like a strict flowchart. At each branching node in this graph, the algorithm looks at a specific feature of your data. If the value is below a certain threshold, boom, the data goes down the left branch. If it's higher, it heads down the right branch. And this branching just keeps happening until the data hits the very end, what we call a leaf node, where a final class decision is made. Moving on to section 2, the ID3 algorithm process. Now, what's really interesting here is the word non-parametric. You know how a lot of classic machine learning algorithms, like linear regression, are always hunting for a single mathematical formula, like an optimal set of parameters to fit the data? Well, ID3 doesn't do that. It optimizes its criterion. Specifically, it approximately maximizes the average log likelihood by constructing a structural, non-parametric model. So instead of spitting out an equation with weights and biases, it literally builds a probability structure to predict if an example belongs to a certain class. So how does it actually pull this off? Let's turn this abstract process into a really simple mental checklist. First up, ID3 starts with a single root node that holds every single piece of data you've got. Second, it searches through all the features in your dataset and all the possible thresholds for those features. Third, it evaluates what would happen if it actually split the data based on those thresholds. And fourth, it picks the absolute best split, divides the data into 2 brand new leaf nodes, and then, here's the kicker, it recursively repeats this entire process for those new leaves. Section 3. Splitting the GANA. Check out the start node here to see this in action. We begin with our whole dataset, which in this case is 12 labeled examples. The ID3 algorithm evaluates the features and decides the absolute best first question to ask is feature 3 less than 18.3? Based on that one question, the data is physically split into 2 separate subsets. It sends the yes examples over to the left leaf and the no examples to the right leaf. It's elegantly simple when you actually see the split mapped out mathematically like this. Which brings us to section 4, entropy, measuring uncertainty. Okay, so how does the algorithm actually know if a split is good? To answer that, we have to talk about entropy. Think of entropy as the algorithm's internal compass. In information theory, entropy is just a mathematical way to measure the uncertainty about a random variable. Basically, the algorithm looks at a pool of data and calculates exactly how chaotic or uncertain it is. To really grasp this, you need to understand the extremes of this chaos. Entropy hits its absolute maximum value, which is 1, when exactly half the examples in a node are labeled 1 and the other half are labeled 0. For a machine trying to classify data, a 50-50 split is completely useless. It's pure uncertainty, basically like flipping a coin. On the flip side, entropy hits its minimum, which is 0, when every single example in the node has the exact same label. 0 uncertainty, perfect order. The algorithm's entire mission in life is to take your data from an entropy of 1 all the way down to an entropy of 0. Burkov summarizes this perfectly in the text. He says, the entropy of a split is simply a weighted sum of 2 entropies. When the algorithm tests out a potential split, it looks at the 2 new leaf nodes it's about to create. It calculates the entropy of the left node, the entropy of the right node, and then combines them into a weighted sum. It'll test thousands of possible splits and simply pick the one that gives the lowest combined entropy. It is literally, mathematically, carving out a path of least uncertainty. Section 5. When to stop growing. Now, obviously, the algorithm can't just loop and split forever. ID3 has 4 strict rules that tell it when its journey is complete at any given leaf. First, it stops if all of the examples in the leaf are classified correctly, meaning entropy has hit 0. Second, it stops if it simply can't find another attribute to split on. Third, it stops if a split reduces the entropy by less than a tiny predefined threshold, essentially if the split just isn't worth the mathematical effort. And fourth, it stops if the tree hits a maximum allowed depth. This is usually set by the programmer to make sure the model doesn't overfit the data. And finally, Section 6, the big picture. Now, we have to talk about a really crucial caveat, which is beautifully captured in this quote from the source material. Because in ID3, the decision to split the dataset on each iteration is local, the algorithm doesn't guarantee an optimal solution. What does that actually mean? It means ID3 is a greedy algorithm. It's kind of like a kid eating the very first marshmallow they see, instead of waiting for a bigger prize later. At every single node, it's only looking for the split that drops entropy the most right then and there. It's not looking 3 steps ahead. Because it's only making these local short-term optimizations, the final tree it builds might actually miss out on a globally perfect, more elegant overall structure. But hey, don't worry, we aren't completely stuck with imperfect trees. We can actually improve the model using techniques like backtracking. This allows the algorithm to undo a split and explore other paths, just to see if they end up building a better overall tree later down the line. But of course, there's a catch. Calculating all those alternative futures takes way more computing time. You're basically trading speed for accuracy. Which leads us to a pretty fascinating final thought for this explainer. Since we know that decision trees like ID3 make purely local, short-sighted choices without guaranteeing a globally optimal solution, how much do we really trust these non-parametric models with complex, high-stakes, real-world decisions? It's an incredible reminder that while machine learning is mathematically brilliant, at the end of the day, it's still just a tool. It's a tool that requires human intuition to guide its parameters and really question its outputs. Thanks so much for joining me on this explainer today, and keep exploring.